Hello everybody, this video is about mARGOt, a dynamic autotuning framework. At first I will introduce the idea of dynamic autotuning and then I will present the mARGOt framework, an adaptation layer for the target application. As an example, I will show how it adapts reactively and proactively the k-means application. We might split the term dynamic autotuning in three different concepts. The first one is tuning. A best practice during the application development is to write parametric code by exposing software knobs that alter the extra-functional behavior of the application, for example in terms of execution time and computation error. Therefore, the tuning process identifies the software knobs configuration that is most suitable for the application requirements. The second term is auto, because we would like to perform such tasks automatically. The third term is dynamic. In this context, we would like to delay the selection of the most suitable software knobs configuration at runtime. Moreover, we would like to continuously tune the application during the lifespan of the process for mainly three reasons. First, the performance may be input dependent. Therefore, we would like to consider the actual input in the decision process. Second, the performance usually depends on the underlying architecture and system workload. For instance, it might depend on the computing resources assigned to the application, which may vary according to the system evolution. Third, the application requirements might change at runtime according to external events or stimuli. To address this problem, we propose the mARGOt autotuning framework. This picture depicts the overall structure. If we focus on the functional domain, we might notice how the application reads a stream of inputs, it performs an elaboration, generating a stream of outputs. For simplicity, in this example the application is composed of a single kernel. However, mARGOt can address application composed of several independent kernels. If we focus on the extra-functional domain, the core of mARGOt is the manager, which continuously provides to the application the most suitable software knobs configuration, by using application knowledge to drive the selection process. The first adaptation mechanism is reactive, which means that mARGOt might change the most suitable configuration to react on changes of both the application requirements and of the behavior observed by runtime monitors. For example, if the throughput monitor notices a degradation of the performance, the manager will try to select a faster configuration to compensate. The second adaptation mechanism is proactive, which means that mARGOt will consider the features of the current input when it selects the most suitable configuration for the target application. In the remainder of the video, we evaluate the benefits of this adaptation mechanism for the end user. It is possible to find all the material used in this video at the following Git repositories, along with a detailed step-by-step tutorial to reproduce the results. Please remember to generate the dataset before running any experiment. The target application is a modified version of k-means from the Rodinia benchmark. The algorithm aims at partitioning n observation in k clusters, minimizing the intra-cluster variance. The input file contains the n observation with m dimensions, while the application results are k centroids with m dimensions. The application structure is rather simple. Another loop elaborates a set of input files. For each file, we randomly initialize k clusters. Then we assign each observation to a cluster based on distance. Finally, we move the clusters in the center of their observations. In this naive version of the application, the number of iterations is the software knob that we would like to tune. Before starting, we need to define the extra-functional properties of interest for the end users. In this example, we assume that they are interested in two properties: the execution time spent for finding the clusters, and the computation error defined as the difference between the cluster position found using 50 iterations and the cluster position found using the evaluated number of iterations. In this context, we assume that we perform at most 50 iterations of the clustering algorithm. The first step to integrate mARGOt aims at learning the application knowledge. First, we write an XML configuration file with extra functional concerns to generate glue code for minimizing the integration effort. Second, we integrate mARGOt in the application source code using the generated glue code. Third, we collect profile information of the application to learn the application knowledge. In this step, the XML configuration file only describes the monitors that observe the matrix of interest. Please refer to the documentation for the correct XML syntax, which is shown in the right part of the slide for reference. Once that we have generated the glue code, the integration effort is minimal. After the inclusion of the headers and the initialization of the framework, we only have to wrap the region of code to manage, in this case by starting and stopping the monitors. In the next step, we build and profile the application to generate the application knowledge in a live demo. The mARGOt framework ships with an utility tool to assist the application developer in the integration process. To use this tool from the command line interface, it is enough to source an environmental file. Now we can switch to the application repository to start the integration process. The first step is to obtain the mARGOt repository. By default, the utility tool will create a folder named Autotuner in the current working directory. Using the very same tool, it is possible to compile mARGOt along with the glue code generated using the XML configuration file for profiling. All the generated libraries are contained in the Autotuner folder. Now we are able to compile the application using the CMake build system. mARGOt generates package config and CMake finders to ease the integration process. In this first step, the application displays profiling information according to the software knobs configuration. If we use 50 iterations, the execution time is approximately 5 milliseconds, while the error is 0. If we use a lower number of iterations, the execution time decreases while the error increases. By using this version of the application, it is possible to derive the application knowledge as shown in this picture. Each dot represents a software knob configuration. The x-axis represents the computation error, while the y-axis represents the execution time. As expected, the number of iterations exposes a trade-off between the matrix of interest. In the next step, we define the application requirements as a constrained and multi-objective optimization problem. In this way, mARGOt knows how to select the most suitable software knob configuration. In this example, we assume that the end user would like to minimize the computation error, provided that the execution time is less than 10 milliseconds. To implement this change, we have to modify the XML configuration file. In addition to the monitor of interest, we need to introduce 3 sections. The first one describes the problem geometry, defining the software knobs and the matrix of interest. The second section describes the reaction policies. In this case, we would like to use the execution time monitor to check if the application behaves as expected. The third section describes the application requirements defined in the previous slide. To complete the integration process, we need to modify the application source code. In particular, before executing the application kernel, the application must ask mARGOt to update the software knob. Moreover, we would like to avoid to measure the computation error in the production phase. We will show how the application behaves in a live demo. We build the application using the application knowledge gathered in the previous step. In this experiment, all the input files have a constant number of rows. Therefore, mARGOt selects the most suitable configuration only at the beginning of the application. If we look at the execution trees, we might notice how the application behaves as expected. The observed execution time is lower than the constraint and the computation error is 0. In the next experiment, we use the same application with heterogeneous input files. In this experiment, we introduced 3 abrupt changes in the input files. Since we obtained the application knowledge with homogeneous input, the effect of every change is to alter the extra-functional behavior of the application. Therefore, mARGOt changes the software knob configuration to react. If we look at the execution trace, we might notice the reactive adaptation mechanism. When the observed performance is worse than expected, mARGOt exploits the performance accuracy trade-off to satisfy the execution time constraint. When the observed performance is better than expected, mARGOt exploits the performance accuracy trade-off to minimize the computation error. With the previous experiment, we noticed how the execution time depends on the input site. With few changes in the input, the reaction mechanism might suffice. However, if the size of each input might be different, mARGOt has to consider the input size in the decision process. To implement this step in the XML configuration file, we need to notify mARGOt about the new input feature. The input size. From the source code point of view, we need to provide to the code that retrieves the software configuration the input feature. The next experiment shows how the new application is able to adapt proactively. In this experiment, we obtained a new application knowledge that considered the input size. Moreover, the size of each input file is randomly generated. Differently from previous experiments, we might notice how mARGOt adapts the application more frequently. If we look at the execution trace, we might notice the proactive adaptation mechanism. Instead of reacting to the input file, in this experiment mARGOt is able to adapt before violating the execution time constraint. In this video we have seen how to integrate mARGOt in the target application and the benefits of reactive and proactive adaptation mechanisms. The mARGOt Autotuning framework is open source and publicly available on GitLab. Along with the source code, it is possible to find user manuals with complete syntax and semantic of the XML configuration files. Moreover, it is possible to generate Doxygen documentation about the framework implementation detail. Thank you for watching.